Hello everybody, get ready to do lesson 3.6, part 3 of pre-calculus math today. Your classwork, contact me here if you need classwork sheets, homework sheets, etc. And then today, 3.6 nonlinear models, part 3. We have 0 points here on your notebook and 38 points here on your classwork. So have your classwork sheet ready to go here. Okay, for today's bell work, teachers and students, we have write an equation of the parabola in standard form. So we have a parabola here, then we have this parabola here. So students and teachers, give your students about 5-6 minutes on this bell work. Okay, welcome back for the solutions of your bell work for the day. For this one here, your first one up here, you're going to use the vertex form of a parabola. And your negative h here would be negative h would be your x here, which would be of your vertex, would be 3 and then 2. So this will be that form. You're going to solve for a here, and then so you plug in your values, and then you solve for a, and a negative 2 equals a, so you plug that back in up here, back here, and you get negative 2 times quantity x minus 3 squared plus 2 for the first one. And then down here, same thing. We use our vertex form, and our vertex is at negative 2. We're going to solve for a. We plug that into our vertex form down here. Solve for a. A is 1/2. So we have 1/2 times quantity x minus x minus 2 squared minus 2 would be the solution here for your second parabola. Okay, into our first slide here of today's lesson. Example 4, fitting an exponential model to data. So we have a table here. Shows the amounts of revenue in billions of dollars collected by the Internal Revenue Service for selected years from 1963 through 2008. So here is selected years from the not consecutive but selected. Use a graphing calculator to find a model for the data. Then use the model to estimate the revenue collected in 2013. So we're going to project out to 2013 using this data as a regression. So let x represent the year with x equals 3 corresponding to 1963. Begin by entering data. You enter data into your calculator, and then you hit a scatter plot here, and then that scatter plot. So we get a scatter plot. From the scatter plot, it appears an exponential model. It does look like an exponential curve. Would be a good fit. Use the regression feature of the graphing calculator to find the exponential model as shown. And then after we do that, here's a times b to the x. A would be 96.5, b would be 1.07, and then once we do that, we come up with our coefficient determination here at 0.98, and our R factor would be 0.99. So it does look like a pretty good fit here. Our R2 is 0.98. Change the model to a natural exponential. Let's try natural exponential, see if that's more accurate. Here's the original, 96.56 multiplied by 1.076 to the x power. And then we're going to use our natural exponential here, e. So 96.56 e to the natural log 1.076x. E natural log b. And then when we get that, we simplify that, and we come up with 0.073, the natural log of this, of x. So we graph that data in a natural exponential model. R equals 96.56 e to the 0.073x. In the same viewing window as shown here. So here was the original scatter plot, and then here's the natural exponential here. It's pretty close as well. From the model you can see that the revenue collected by the IRS from 63 through 2008 had an average annual increase of about 7%. From this model you can estimate the 2013 revenue to be, again using that, and then we plug in 5.3 here for 2013, substitute 53 for x, and we get this number here, which is more than twice the amount collected in 2003. You can also use the value feature of the graphing calculator to approximate the revenue in 2013 to be 4624.7 billion. So again, that'd be right here. Here is our number here, 4624.24 when x equals 53. So that would be your value there. Let's try one. So here's our modeling data problem here. We have A, use regression feature for this data, and then B, rewrite the model as a natural exponential, and then C, use the natural exponential to predict the number of staples stored in 2009. So we're going to project from this data set, and that's the first part of your, this will be on your classwork sheet here. Okay, so N, using the regression feature for an exponential, from this data set we come up with this exponential model here. Then rewrite the model as a natural exponential, and once we do that we come up with this expression here, 1315.584 e to the 0.0624 t. That's our natural exponential. And then for 2009, let t equal 9 in this case down here, and we come up with this number here for the stores. And then this is for you students to graph it, to visualize, which can also help. Fitting a logistic model to data to estimate the amount of defoliation caused by gypsy moth during a given year. A forester counts the number of egg masses on 1/40th of an acre, which is a circle of radius 18.6 feet in the fall. The percent of defoliation Y the next spring is shown in the table. So this is our defoliation due to gypsy moth. And then these are our egg mass counts here. So the number of X of egg masses on a 1/40th of an acre. And we're trying to see if there's some kind of correlation here between egg masses and defoliation. So using the regression feature of a graphing calculator to find a logistic model for the data, enter the data into a graphing utility using the regression feature of the graphing calculator. So by doing that, once we enter that data in, here's our logistic model here. And then here's our output from that data input for A, and then our B, which is over here, and then our C, which is this number here. Once we get that, our C is about 100, that goes in the numerator. And then we have 1 plus A, which is 7, and then E to the negative C, or B here would be this number here, negative 0.069 x. So there is our model derived from that data set. So how closely does the model represent the data? You can use a graphing calculator to graph the actual data, which is here. It should look like that. And the model in the viewing window, so we do have that. It appears that the model is a good fit for the actual data. enter the data, because the line here follows your plot here, is what it does. Enter the data into a graphing calculator using the regression feature of the graphing calculator. You can approximate the logistic model to this right here. So again, by using the regression feature, we can, it seems like it correlates with this model. You can see how well the model fits the data by comparing the actual values of y with the values of y given by the model, which are labeled y asterisk in the table below. So here's the y, and then this is the model y here. So they're pretty close. Pretty close. In the table, you can see the model appears to be a good fit. So again, it seems like it is a pretty good fit for that. Using your regression, it seems to correlate with the actual. Then that way you can project out into the future with it. Okay, so our modeling data, again, another issue here. We have percents P of women in different age groups who have been married at least once. So here's our age group here. Using a regression feature of a graphing calculator to find a logistic model for the data, let X represent the midpoint of the age group. Then we have a grid down here. So by plugging this in to your calculator and then using your logistic model regression function, you should come up with this expression here of a logistic model by using your regression. Then use the regression feature. See, so you're using the mid-range here of your age group. 20 and 24 would be a 22, etc., etc. And then this will be your output here. Then this is what your graph should look like from this date, from this model. This model would be the line, and then the plots here would be from the model itself, is what it should look like. And the conclusion would be the model fits the data pretty well. So it does seem